Welcome back. In the last video, we uh, found that the length of the line segment from pi minus 1 to pi is given by the square root of x of ti minus x of ti minus 1 squared plus y of ti minus y of ti minus 1 squared. In this video, we will further evaluate this length, and we are going to get help from the mean value theorem. So let's look at the function x of t, and we are concentrating on the interval from ti minus 1 to ti. We recall that we assumed that the vector function r is differentiable. So as a result, we can assume that x of t is differentiable over this interval. So by the mean value theorem applied to the function x of t on the interval from ti minus 1 to ti, we can say that for some ti star in this interval, x prime of ti star is equal to x of ti minus x of ti minus 1 over ti minus ti minus 1. So recall that the mean value theorem simply says that the average rate of change of the function over an interval is the same as the instantaneous rate of change of the function at some point in that interval. So this equation is what we get if we apply the mean value theorem to the function x of t on this interval from ti minus 1 to ti. So from this equation, we see that x of ti minus x of ti minus 1 is equal to x prime of ti star times ti minus 1. So by applying the mean value theorem, we obtain this this expression for the quantity x of ti minus x of ti minus 1, which is what we have in this inside the square root for the length of the line segment from pi minus 1 to pi. Now we can apply the mean value theorem to the function y, and we can also come up with a similar expression for this difference here. So by the mean value theorem, again, you can obtain that y of ti minus y of ti minus 1 is equal to y prime of si star times ti minus 1, where si star is a number in the interval from ti minus 1 to ti. What we're going to do is we are going to look at the length of the line segment from pi minus 1 to pi, which is equal to this expression. Now here, x of ti minus x of ti minus 1 can be replaced with the quantity here, x prime of ti star times ti minus 1. And then similarly, y of ti minus y of ti minus 1 can be replaced with this quantity here. So let's do that. If we do that, we get the quantity square root of x prime of ti star squared multiplied by ti minus 1 squared. Again, we are simply replacing this by that. So if you square that, you're going to square this. This is what we get. And y of ti minus y of ti minus 1 would be squared would be y prime of si star squared times ti minus 1 squared. Now at this stage, I am going to replace ti minus 1 by delta t. That is, I'm letting delta t to denote this difference from difference ti minus 1. So this would be my delta t here. So this is what we get. And actually, let's make it delta ti. And then what we get is this expression where now we can factor out delta ti squared. And if we factor out delta ti squared outside of this square root, then we end up with the root of x prime of ti squared plus y prime of si star, x prime of ti star squared plus y prime of si star squared multiplied by delta ti. Okay, so then we got this. So then recall that in the last video, this is the expression that we got for the length of the line segment from pi minus 1 to pi, and now we have obtained the following expression for the length of this line segment. So the length of the line segment from pi minus 1 to pi, after we have applied the mean value theorem, is equal to the square root of x prime of ti star squared plus y prime of si star squared multiplied by delta ti. Now, so if you recall that the length of the curve is the limit as n goes to infinity of this sum. We have computed the length from pi minus 1 to pi, so we're going to replace the expression that we got here, and so the length of the curve would be the limit. The length of the curve would be the limit as n goes to infinity of the sum I going from 1 up to n of the length of the segment from pi minus 1 to pi. We obtained an expression for that, which is equal to the root of x prime of ti star squared plus y prime of si star squared times delta t I, and then this limit that we have here is the same as the limit here. Now notice that the only difference we have here is that I am replacing the si star by ti star. See, when n goes to infinity, the interval is from ti minus 1 to ti is so tiny, so recall that ti star and si star are in this interval. So when n is big, when you pick a lot of points on the curve, then these intervals are so tiny that ti star and si star would be almost the same. So in the limit, I can say, well, these two are the same. And now if I look at this, so what we have obtained then is that the length of the curve is the limit as n goes to infinity of the summation I going from 1 up to n, root of x prime of ti star squared plus y prime of ti star squared times delta t. And this is the Riemann sum of the function x prime of t squared plus y prime of t squared. So as a result, this limit will be equal to the integral from a to b of the function root of x prime of t squared plus y prime of t squared dt. So finally we conclude the following. If C is a curve parameterized by the vector function out of t equal to x of t comma y of t, where t is between a and b, and then the length of C is equal to the integral from a to b of the square root of dx dt squared plus dy dt squared dt. Now recall that dx dt and x prime of t, they are the same thing for same notation for the derivative of x. Of course, as we did this, we made some assumptions, which you can find in the first video. Similarly, even though my entire discussion, we picked a curve in the plane, but even if we have a curve in the three-dimensional space, then the length formula doesn't change much, except that we now have dz dt squared inside of the square root. Now, in fact, we can talk about the length of a curve in dimension 4 and 5 and so on in the same way. Okay, so we have obtained the length of the curve C, and we have this nice clean formula for the length. So if we know the derivatives of the components of R, then we can go about finding the length by evaluating this integral. Okay, so what's going to come up in the next video is applying this formula for some given curves.